Welcome to the E-Pathshala lecture series in computer science. We are dealing with the course computer architecture. Today we look at what is meant by the fixed point arithmetic unit. So, the learning objectives are to discuss how the various fixed point arithmetic operations like addition, subtraction, multiplication and division are carried out in the processor. So, all of you all know that an arithmetic logical unit is responsible for performing the arithmetic and logical operations in the processor, and it is a fundamental building block in the central processing unit or the CPU of the computer. So, first of all we look at the basic operation of addition. So, when you look at an addition operation, the basic block is a full adder circuit. So, a full adder circuit takes 3 inputs and binary inputs and produces 2 binary outputs, a sum output and a carry output. So, the truth table of a full adder circuit has been shown here, and this is the circuit of a full adder circuit. So, if you look at the sum bit getting generated, the sum is an XOR of these 3 bits. It is an XOR of x, y and the carry in, and the carry is generated as a sum of these 2 terms and the product of these 2 terms and the sum of the product terms according to this truth table. So, if you look at a subtractor to be implemented from an adder, so instead of using a separate subtractor, it is also possible to use a separate subtractor where you can, just like how you have a full adder, you can form the truth table for a full subtractor and implement it. But normally what is done is, that negative numbers are represented in the complement form, more preferably in the 2's complement representation, and an adder unit is enough to perform subtraction also, because a subtraction operation can always be converted into an addition. When you have to do an a minus b, it can be written as a plus minus b. So, it is enough if you have a combined adder subtractor unit to do the subtraction operation. So, if you see how this is done, you have a normal full adder circuit here. One input to the full adder is given as such. The second input to the full adder, if you see, the second bit is XORed with a control input which is called the sub bit. So, if you have to perform a subtraction operation here, you make this bit 1, and if you have to perform an addition operation, you make this bit 0. So, if you make this bit 0, what happens is a 0 and a XOR of 0 produces an output of 0. Similarly, a 0 with an XOR of 1 produces an output of 1, which means the second bit b is passed as such without any changes when an addition has to be performed, that is when your sub signal is 0. On the other hand, when you make this bit 1, that is a subtraction operation is on, a 0 and a 1 will give you an output of a 1, and a 1 and a 1 will give you an output of a 0, which means whatever is given is in b is getting complemented here. So, you find the 1's complement of this value and give it to the full adder circuit as a second input. Now, you know that the 2's complement of a number can be formed from the 1's complement by just adding 1 to it. Now, that 1 gets added here when you give the add sub signal as the third input here. So, if it is a subtraction operation, this line also becomes a 1. So, that 1 gets added, this produces the 1's complement of the number. So, 1's complement plus 1, that will give you the 2's complement of the number. So, what gets added is not just the number, it is the 2's complement of the number, and so it produces the subtracted value. And if you have to detect for zeros, you just have a circuit which will check whether it is a 0, that is called a zeros detector, and produces the output. So, you can perform a combined operation of addition and subtraction using this circuit. So, if you look at the construction of a 32-bit adder here, now as we saw in the full adder circuit, the full adder circuit is capable of doing addition of one stage, where you take 3 inputs and produce one output as sum and the other input as carry. Now, if you have to have a 32-bit adder getting constructed, I need such 32 stages of such full adders. Each of these take x naught, y naught, etc. up to x 31, y 31 as inputs, and the input carry is c naught. So, this full adder will perform its operation produce a sum bit and it will produce a carry bit, and once the carry bit reaches here, this full adder circuit has all the 3 inputs. So, it will add these 3, produce a sum bit and a carry bit, and so on. So, this is what is called a 32-bit adder circuit. Now, instead of a 32-bit adder, if you have to construct a 64-bit adder, then you just have to increase the number of stages to 64. Now, if you look at the critical path here, this is the critical path of your full adder circuit. That is the longest path, the path which takes the longest time to traverse in the circuit is normally called the critical path. So, it is the last sum bit that is getting generated. So, that is your critical path. Now, in this circuit you also have to look at overflow detection. What is overflow? Overflow is normally when the data is too large or too small to represent using the number of bits that you have used. Say for example, if you are looking at a 4-bit number for representation and assume that you have 2's complement representation, then if your number is greater than 7 or it is less than -8, it cannot be represented. So, this is the range of numbers +7 to -8 is the range of numbers that you can represent using a 4-bit binary representation. So, if it goes beyond this representation, you say that an overflow has occurred. Now, when you look at an adder-subtractor circuit, when you try to add 2 numbers of the same sign, you will land up with problems. When you try to add numbers with 2 different signs, a positive and a negative number, then obviously overflow is not going to occur. But when you try to add 2 positive numbers or when you try to add 2 negative numbers, then there is a possibility of overflow, and overflow is said to occur when you add 2 positive numbers and you get a negative result instead of a positive result, or you try to add 2 negative numbers and you get a positive result instead of getting a negative result. This is a condition, this is an overflow condition. Now, how do you detect overflow? Overflow is normally detected by looking at the carry that goes into the most significant bit and the carry that comes out of the most significant bit. These 2 should be the same. If there is a carry going into the most significant bit and there is no carry coming out of the most significant bit, that is an indication of a carry overflow condition. So, overflow can be just detected by doing an XOR of these 2 bits. So, when these 2 bits are different, you get an XOR output of 1 indicating that an overflow has been detected. Now, the 32-bit adder that I showed you all earlier is normally called a ripple carry adder. That is because you find that every adder unit, full adder circuit gets the inputs, produces a sum bit, produces a carry bit, which is then used by the next circuit. So, as the carry ripples from one stage to another, it is called a ripple carry adder. And in the case of a ripple carry adder, the delay obviously depends upon the number of basic units, because every basic unit generates a sum output and a carry output. A sum is a sum of products expression of your inputs x and y and the carry input, and a carry is again, the carry out is again a sum of products expression of these 3 bits. Any sum of products evaluation will take 2 delays. So, every basic unit is going to take 2 delays, which means that if you are looking at a 32-bit adder circuit, I am going to have such 32 such blocks. So, the delay is going to be 64. So, if you have an n stage adder, the delay is going to be n into 2, which is obviously very high for large adders. So, what do we do to solve this problem? Fast addition is normally looked at using the concept of carry look ahead adder. Now, the problem with the ripple carry adder is that every stage will have to depend on the previous stage to finish its operation and generate the carry bit. So, the carry bit is the one that is causing the delay, and that is why it is called a ripple carry adder. Now, if we make an observation here, you know that carry out is nothing but P into carry in or A into carry in or A into B. So, A, B, C, it is just the product of these terms, respective products of these terms. Now, and you know the C out 1, the carry out 1, that is the carry out from the first unit is going to go as input to the second unit, and the carry out 0 is going to go as input to carry in 1. So, if you look at this expression where C in 2 is represented as this expression, you have a C in 1 here, but C in 1 is nothing but C out 0. So, if you just substitute that in this equation, you have an expression which does not involve your C in 1 at all. You find that everywhere it is just C in 0, C in 0. C in 0 is nothing but the input carry bit that you passed on. So, the input carry bit is always available, your C naught carry input is always available, and all your A's and B's are always available. What is not available is the intermediate carries, your C1 in or C in 1 2, C2 in, so on and so forth. So, now if you are able to replace your C in 1 with the C naught and get an expression which has removed all the intermediate carries and which depends only on A, B and C naught, it is easier to design. You do not have to wait for the previous carries to arrive. You can just evaluate this based on whatever is already available, and all this is available simultaneously. So, in order to do this carry look ahead addition, we normally define two terms. One is what is called a GI, which is a generate function or a generate bit, and the other one is a propagate function PI. Now, GI can be defined as AI into BI, and PI can be defined as AI XOR BI. So, in your expression for carry out, if you find that you have wherever you have an AI, you can replace it by a GI, and wherever you have an AI plus BI or an that can be replaced by AI XOR BI. So, based on that, any carry function can be written like this. So, if you have an A B and you have a C out, when you have your inputs both as 0 and 0, your carry output is anyway going to be 0. So, that is called the kill. And if it is a 0 and 1, if your inputs are 0 and 1, you know that only if your C in becomes 1, that will combine this 1 and it will produce a carry output of 1. So, that is called the propagate function. So, when you have a combination of C 0 and 1, if your C in becomes 1, then that gets propagated. Similarly, for 1 and 0 combination also, only if your C in is 1, it will get propagated. But if you look at the last combination of 1 1, irrespective of the carry bit here, carry input bit here, it is anyway going to generate a carry bit. So, that is called the generate function. So, that is how you distinguish between a generate function and a propagate function. So, if you look at this block here, your output carry can be written as a generate function plus the input carry into the propagate function. So, if you look at any of these blocks, if you look at this block for example here, when you have a carry generated out of this block, it is either that this block itself generated the carry bit independently irrespective of the carry input that comes in, or it just propagates the carry input that is passed on to it to the next stage. So, at every stage you can look at it that way. Say for example, you are looking at this block, you have a carry getting generated out of this block. It is either that this block itself generated the carry using your A1 and B1. So, if both A1 and B1 are 1s, then this block itself is going to generate the carry bit. On the other hand, if only one of them is a 1, then it will combine with the input carry bit that comes in and it will try to propagate this carry. So, that is also possible. So, your carry out can generally be written in terms of the generate function and the propagate function, and this holds good for any block. So, if you look at a 4-bit adder like this, a 4-bit carry look ahead adder, any adder, if you look at the carry out from the last stage here, it is either that this block itself generated the carry bit, or this block generated it and this block propagated it, or this block generated it and these two blocks propagated it, or it was this block that generated it and it was propagated by the other blocks. So, all this can be written in terms of the input carry bit and only the data input signals. Now, that is the advantage of a carry look ahead adder. The main disadvantage of a carry look ahead adder is because every expression, every carry out expression can be written in terms of only the input carry and A and B, it is only a sum of products expression. So, irrespective of which carry you have to generate, it is only going to take 3 delays, 2 delays for generating the carry bits and 1 delay after that to generate the sum bit. But the drawback of your carry look ahead adder is that as the number of stages increases, the number of inputs that go to your AND gates and OR gates becomes very, very large. So, you have a fan in fan out constraints coming into picture, and it is not practically feasible to implement this circuit. So, we look at what is called a partial carry look ahead adder, which makes the implementation of this circuit practical. So, what we try to do here is we try to look at combining basic blocks which are practical. Say for example, if you have to build a 32-bit adder circuit, you can construct it as having 8 units of 4-bit adder blocks. So, that is a possibility. Say this block diagram shows that, say for example, a 32-bit adder circuit can be either represented with 8 units of 4 bits each or 4 units of 8-bit carry look ahead blocks. So, I have an 8-bit carry look ahead adder here, another 8-bit carry look ahead adder, so on and so forth, and all of them combined together will generate a 32-bit carry look ahead adder. Now, this is the input carry to this block, C8 is the input carry to this block, C16 is the input carry to this block, and C24 is the input carry to this block. A partial carry look ahead adder combines a ripple carry addition and the carry look ahead principle. So, what happens here is inside this block all the carries are getting generated using carry look ahead addition, but the carry across these blocks or the interblock carries are being rippled. So, C8 will be generated and C8 will be rippled to the next stage. So, only after C8 becomes available here, this block starts operating. So, the interblock carries are being rippled here and the intra-block carries are getting generated using carry look ahead addition. So, if you do look at the delay here, each of these will take only 3 delays or 2, rather for carry it is only 2 delays for generation, but only after this generates C8 this can start operating, because this will take this as C0. So, this will take 2 further delays, this will take 2 further delays and this will take 2 further delays. So, as you keep increasing every module will add just 2 delays to the circuit. That is the delays for the carry, and once the carries get generated, you will have to generate the sum bits. Now, the other option is, that is one option of practical implementation. The other option is you can look at a cascaded carry look ahead adder. So, this is at a more abstract level, where what we try to do is the multiple adder units that we talked about, your 4-bit adder or an 8-bit adder, can as such be treated as a single block, and we talk about the carry look ahead principle being applied at higher levels also. So, for example, when I am looking at a carry that is generated out of this 4-bit adder block, it is either that this 4-bit adder block generated it, or this 4-bit adder block generated it and this block propagated it. So, whatever concepts we applied to independent stages of full addition, we will apply the same principles of carry look ahead addition to blocks of full adders. So, this is a 4-bit adder. So, at every stage when you want a carry getting generated out of this block of 4-bit addition, either this generated it, that is the generate function for this block, or this block generated it and this block propagated it, or this block generated it and these 2 blocks propagated it, or this block generated it and these 3 blocks propagated it, or it was just the input carry that is being propagated by all the 3 blocks. So, you can write a higher level carry propagate function or carry function for this type of carry look ahead adder, and this concept can be extended to any levels. So, that is how you can look at cascading this principle to higher levels of carry look ahead addition and make it practically possible. Now, the next concept that we are going to look at is how do we make use of carry save addition. Just like how you have carry look ahead addition, you also have the concept of carry save addition. Now, normally when you look at a full adder circuit, you know that a full adder can only take in 3 inputs at a time. So, you take 2 data inputs and reserve the 3rd input for the carry input that comes in from the previous stage. So, that is why your ripple carry adder and all that gives you a problem. Now, what we try to do is in the case of carry save addition, when you have to add these bits, what you try to do is you add all the 3 bits together and generate a sum bit and generate a carry bit. So, instead of adding two data bits and a third carry bit, you add all the 3 data bits together. So, add the columns first. So, add the 3 data bits, you have a sum bit getting generated and you have a sum vector getting generated, and these two, sum vector and the carry vector, will then be added together. Say for example, when you look at a full adder circuit, you only have 3 inputs given to it and it produces 2 outputs. So, you can do a parallel implementation of all this reduction from 3 to 2, and this can be used to reduce the critical path of basically the multiplication operation, which we are going to discuss later on. So, this you will find that if you have to do a 53 bit multiply for floating point operations, in the case of your normal addition, it will require at least 53 levels of addition, whereas with the carry save addition it require only lesser number of stages. So, this is what I discussed. So, you can combine 3 data inputs together. So, these 3 can be combined together. So, suppose if I have to add 6 data bits, then what will happen is 3 data bits can be added together, that will produce a sum bit and an appropriately shifted carry vector. Similarly, these 3 added together will produce a sum vector and an appropriately shifted carry vector. So, I have that has been reduced to 4 vectors now. Now, at the next level of carry save addition, combine these 3 together. So, it will produce again a sum vector and a carry vector. This carry vector is carried on as such. So, you now have again 3, which can again be combined using the next level of carry save addition. So, at every level you can have multiple carry save adders brought in, depending upon the number of data bits that you have to add. So, instead of 6 data bits, if you have 9 data bits, then I will have to use 3 carry save adders at the same level, and depending on how it keeps reducing, you can keep increasing the number of levels. So, this is typically how carry save addition gets done. So, this is a circuit which shows you how the carry save addition gets done. The next concept that we are going to look at is binary multiplication. So, in the case of binary multiplication, this is the paper and pencil of binary multiplication. What you try to do is you look at the least significant bit of the multiplier, and depending on whether it is a 1 or a 0, you are going to either replicate all zeros here or replicate the multiplicand as such. Then you look at the next bit of the multiplier. If it is a 0, introduce zeros here. If it is a 1, replace the multiplicand here. So, these are the partial products that you form. So, every partial product is either going to be the multiplicand as such, shifted appropriately, or it is going to be zeros if the multiplier bit is 0. Once the partial products have been formed, you just have to add all the partial products, you will get the final product. And always remember that when you try to multiply 2 n bit numbers, you are going to get a 2n length product. Now, if you look at a combinational multiplier for unsigned numbers, a combinational multiplier looks exactly how your paper and pencil method happens. So, the structure of a combinational multiplier is the same as that of the paper and pencil method. So, you have initially you have all zeros given because there is no carry bit that has to be given here. So, this is the first partial product, this is the second partial product that is going to be formed. So, each of these bits you have an AND unit here, which will AND the multiplier bit with the appropriate multiplicand bit and either produce a 0 or a 1 depending on what your multiplier bit is. So, if your multiplier bit is 0, it will produce a 0. If your multiplier bit is 1, it will just replicate that multiplicand bit. So, you have that operation being done here, and the full adders, each of these is a full adder after forming the partial product. So, each of these adds up the appropriate partial products. Shifting is obviously done by means of the structure itself. So, if you see these basic units are here, the next basic units are shifted by 1 bit, the next basic units are shifted by 1 bit, so on and so forth. The shifting or the structure of these basic units basically takes care of the shifting operation, and you just form partial products. So, the partial products are formed here, it is added with 0 because that is the first partial product and it is passed on here. Now, this gets added with a new product that is formed. the earlier product, whatever carries got generated there will get added here, and whatever final products will have to be generated are generated here. So, when you try to multiply two 4-bit numbers, you get a product which is an 8-bit product. So, at every stage it accumulates a into 2 power I if the corresponding multiplier bit is a 1. This is how unsigned combinational multiplier works. Now, if you look at a sequential multiplier unlike a combinational multiplier, this is the algorithm for a sequential multiplier. So, you have a multiplicand which is a 32-bit multiplicand, you have a multiplier which is a 32-bit multiplier, you have an ALU unit which is a 32-bit ALU unit, and finally, your product is formed here. The product is going to be a 64-bit product. So, what you do is at every point of time, you take one bit of the multiplier, do a shifting operation here, check whether the multiplier is a 1 or a 0, and depending on the multiplier being a 1 or a 0, you either add the multiplicand to your product and then shift it right, or just shift the product to the right. So, initially you have the ALU, you have all zeros here in the product field. So, what happens is the first partial product is formed by adding to the zeros, either adding the multiplicand or adding all zeros depending upon what your multiplier bit is. Once the first partial product is formed, you do a shift right operation. So, that one bit of it moves on to this position in the product register, and the multiplier bit which has already been tested and added appropriately is shifted out. So, the next position what will happen is the multiplier bit that is currently to be tested comes to the least significant bit position. So, at every point you check the last bit, that will tell you whether the corresponding multiplier bit is a 1 or a 0. Accordingly, if it is a 1, you add the multiplicand to the partial product and then shift it right, or simply add zeros to the partial product and shift it right. And this process has to continue for 32 bits because you are doing a 32 by 32 multiplication, and this is what is called a sequential multiplier. So, the sequential multiplier algorithm is shown here. This is the same as I discussed earlier. So, initially you have a product of 0. So, you check the multiplier bit, and depending upon the multiplier bit being a 1 or a 0, you add the multiplicand if it is a 1 and then do a shift right, or just add zeros and do a shift right. So, do it 32 times and then stop your operation. The final product is available in the product register. So, now if you look at signed numbers multiplication, you just have to remember the rules of arithmetic. The simplest way of handling it is you just treat them as positive numbers, multiply, and then depending upon whether the signs of the two numbers are different or the same, you fix the sign of the result. So, you do not have to have any complicated algorithm to do it, but only thing is you need to check the sign bits and you will have to handle it. So, if you look at multiplication of signed numbers, so to summarize, we have looked at various fixed point arithmetic operations in this module. We started off with binary addition, we looked at how a full adder works, and using a full adder how we can construct different sizes of a ripple carry adder. It is called a ripple carry adder because the carry ripples from every stage to the other stage. So, the delay is very high here. So, we next looked at what is called a carry look ahead adder, which uses the principle of carry look ahead addition in order to reduce the delay. And we also saw different forms of implementing this carry look ahead adder because a pure carry look ahead adder has practical limitations. Then we looked at what is called a carry save adder, which saves the carries generated at every stage and adds them at the appropriate positions in the next stage, which is going to be very useful when you do multiplication. And then we looked at how subtraction can be done with the help of addition itself by finding out the 2's complement of a number and adding. Finally, we saw how multiplication can be done. We looked at the paper and pencil method of binary multiplication, and then we saw how a combinational binary multiplier can be implemented, and we also looked at how a sequential binary multiplier can be implemented. Thank you.